Einstein postulated that mass causes the curvature of space-time without explaining the underlying mechanism. This article suggests a quantum mechanical model of how a fermion, like an electron's electrostatic field, interacts with space-time's nonlinearity through the optical Kerr effect to create the gravitational curvature of space-time. This article will also address how gravity affects most everything in the universe, including the rate of time, the speed of light, energy, and our three spatial dimensions. Understanding quantum gravity can also provide a new perspective of what is inside a black hole, and also provide another interpretation of the cosmological redshift and the need for dark energy. This model of quantum gravity can help unify both general relativity and quantum mechanics. Since there is not a consensus definition of space-time or a particle, and how forces like gravity and fields like the electromagnetic field are created, I will refer to John A. Macken's model of the universe paper called Oscillating Space-Time, the Foundation of the Universe, as my starting assumption. This model suggests that the universe is composed solely of four-dimensional space-time, length, width, height, and time, with all matter, energy, forces, and fields being manifestations of its properties. This is a wave-based model. Planck units are used at the quantum level, like the Planck length, which is extremely small, at a length approximately 1.6 times 10 to the minus 35 meters, making it the smallest measurable length in the universe. It is about 20 orders of magnitude smaller than a proton, and a proton is about 20 orders shorter than 62-mile distance. And you are about 20 orders magnitude shorter than the distance to the Andromeda galaxy. Planck units are a system of natural units defined using fundamental properties of nature, including the speed of light, gravitational strength, and energy of a photon. A wave-based model requires a medium to have a certain characteristics to support waves and its propagation. It must be elastic, meaning having the ability to absorb energy and return energy as a wave propagates through it. They also need to have resistance to allow for energy to be generated, and they usually exhibit nonlinear characteristics when strained beyond their linear ability. Nonlinearities exhibit a more complex relationship between stress and strain. Nonlinearity can lead to the introduction of additional frequency components in the wave, which can cause the sinusoidal wave to distort. Nonlinearities can have both positive and negative effects. In sound, waves propagate in air. Nonlinearities occur that slightly modify the original waveform. The finite air pressure sets a boundary condition that creates a very weak nonlinearity at conversational levels. The second-order harmonic distortion refers to the addition of sound wave at twice the original frequency. Second-order distortion in sound can add a warm, rich, and slightly fuzzy sound to the audio, making it more pleasant to listen to, while a third-order harmonic is considered harsher and edgier sounding. In water, the breaking water waves are considered to be a nonlinear characteristic of water. This can lead to erosion or an enjoyable time for surfers. In light, the light refraction is often considered a second-order distortion due to light interaction with the medium through the optical Kerr effect. A mirage is a real optical phenomena that gives a false position of an object where the second-order distortion from an electron's electrostatic field in oscillating space-time, as postulated in this article, creates gravity curving space-time. Gravity is described by the general theory of relativity proposed by Albert Einstein in 1915, which describes gravity in terms of the curvature of space-time caused by the uneven distribution of mass. Einstein just postulated that mass causes the curvature of space without explaining the underlying mechanism. He also further established the speed of light is constant in a vacuum. The current consensus is that gravity does not slow the speed of light. With this as assumption, then the answer to why it takes longer for light to travel around a mass is due to the curvature of space-time creating a longer path for the light to travel. One problem with this assumption that gravity does not slow the speed of light is gravitational time dilation. That tells us gravity slows the rate of time. As a result, time runs slower in regions of stronger gravitational fields. This means that a clock located closer to a massive object will tick more slowly than a clock situated further away. With the rate of time directly related to speed, speed equals distance traveled per unit of time, shows that gravity does slow the speed of light. This model postulates that gravitational curvature of space-time can be thought of as the slowing in the coordinate speed of light and bending the path of light by the optical Kerr effect. The speed of light is not constant. This model also confirms with gravitational time dilation, where gravity slows the rate of time, which slows the speed of light. An optical Kerr effect, all transparent materials exhibit nonlinear effect. The atoms that form a transparent material are bound by electric fields with a finite strength. Once this finite strength is exceeded by an electric field, such as from light or later shown from a particle that creates gravity like an electron, it produces a nonlinear optical distortion that results in a change in the index of refraction to the material. The refractive index determines how much the path of light is bent or refracted and how much the speed of light slows. The refractive index may vary with wavelength. This causes white light to split into constituent colors when refracted. Some examples of the speed of light in different mediums, like in a vacuum, speed of light is 299,792,458 meters per second, and that's in zero gravity. In air, we have, it gets slower, the refractive index is a little higher. Water, we have a refractive index of 1.33, which is even higher. Glass, 1.5. Refractive index, where the speed has been reduced to 199,861,639 meters per second. And in a Bose-Einstein condensate of ultra-cold sodium atoms, scientists were able to slow the speed of light down to 17 meters per second. That's 38 miles per hour. So the refractive index is always positive, meaning that any number higher than 1 slows light from the vacuum index of 1. This change in refractive index is proportional to the square of the electric field intensity, which can be mathematically expressed as a change in the index of refraction in space-time equals the wavelength of the light times the Kerr constant, which in oscillating space-time or vacuum is 1, and E is the strength electric field squared. Now let's talk about oscillating space-time. The oscillating space-time is postulated to be the single universal field medium that is responsible for all matter, energy, forces, and fields to exist. Oscillating space-time is a refined version of John Archibald Wheeler's model of the universe, where he envisions the fabric of the universe as a chaotic subatomic realm of quantum fluctuations on the order of Planck length, which he called quantum foam or space-time foam. Oscillating space-time is visualized as a quantum mechanical wave propagating medium composed of individual rotating dipole waves that have a Planck volume maximum lobe that expands proper volume and increases rate of time, and a Planck volume minimum lobe that decreases proper volume and decreases rate of time. These Planck volume lobes determine the 3 spatial dimensions, length, width, and height, and define space in space-time. The rotating frequency, which is the Planck frequency of the dipole waves, defines time in space-time. This ties space and time together. Oscillating space-time oscillators have a Planck angular frequency of about 10 to the 43 radians per second. and they do not possess angular momentum since they are the space-time medium. Rotating dipoles that do possess quantized angular medium would include our 17 fundamental particles, each having different wave frequencies lower than the space-time oscillators. For example, an electron angular frequency is 7.76 times 10 to the 20 radians per second. Some characteristics of oscillating spacetime include, that is elasticity. Oscillating spacetime can be likened to a rubber sheet that can stretch and bend. Its elasticity allows it to be influenced by energy and mass, causing it to warp and stretch in response to matter. This means it has the ability to absorb energy and return energy as a wave propagates through the medium. It's also a nonlinear medium, viewed as a nonlinear medium, meaning its properties change in the presence of energy and mass. This nonlinearity is responsible for the creation of particles and forces, including gravity. Has to have impedance. The impedance of space-time is so large that even a small strain amplitude produces a very large intensity for a given frequency. This enormous impedance of space-time can only be achieved if space-time has a large energy density implied by zero-point energy. It also determines the speed of light. The space-time oscillators impose a local rate of time and generate constants like the speed of light, gravitational constant, and the reduced Planck constant. The speed of light is calculated to be about 299,768,000 meters per second, which is the speed of light equals Planck length times Planck frequency. Space-time oscillator low volumes and rotation frequency are reduced by the strain of gravity. The reduced low volumes cause our three spatial dimensions to contract and the rotation frequency to reduce in the rate of time, which causes the speed of light to reduce. Note that when the measuring equipment that has an oscillator, which is a timing clock, is in the same gravitational potential than the speed of light being measured, we'll always measure light as being constant. The oscillating space-time must have curvature. Gravity in oscillating space-time bends or curves light by the optical Kerr effect and slows the speed of light. This leads to gravitational lensing, where light bends around massive objects. This provides a quantum-based rationale for the curvature of space-time, connecting general relativity with quantum mechanics. Single relativistic force. All forces, gravitational, electromagnetic, strong, and weak, are manifestations of a single relativistic force. Relativistic force refers to the force experienced by an object moving at speeds close to the speed of light, necessitating modifications to classical mechanics to account for relativistic effects. And oscillating space-time has superfluid characteristics. It's vision that to have the characteristics of a superfluid like a Bose-Einstein constant. A superfluid has zero viscosity, which therefore flows without any loss of kinetic energy. When stirred, a superfluid forms vortices that continue to rotate indefinitely. Now here's a simplified electron particle. So it is postulated that particles in oscillating space-time are rotating dipole waves that have quantized angular momentum and a specific amount of energy. The stability and mean lifetime of each of the 17 fundamental particles depends on how well their rotation frequency is compatible with the resonance frequencies in oscillating space-time. For example, the estimated mean lifetime of an electron is around 66,000 yodel years, which is at least 5 quintillion times the age of the universe, making this a very stable particle. Muon, which is similar to an electron, has a measured mean lifetime of about 2.2 microseconds, so its resonance in space-time is not as good. And a Z boson mean lifetime is estimated to be about 10 to the minus 26 seconds, so its resonance in space-time is not good at all. The rotating electron core modulates or distorts space-time in 4 dimensions: 3-dimensional volumetric, Planck length modulation of spacetime and also modulates the rate of time. This is accomplished where one portion of the lobe, the spatial maximum lobe, expands proper volume and slows the rate of time relative to local flat spacetime. The opposite lobe, spatial minimum lobe, reduces the proper volume and increases rate of time relative to local flat spacetime. The difference in rate of time and volumes between these two lobes create a strain gradient within the electron core and the outside of the core. The electron has a constant angular frequency of about 7.76 times 10 to the 20th radians per second, with a circulating power of about 64 million watts. And it has an energy of about 8.187 times 10 to the minus 14 joules. Now we'll look at the electron standing rotating wave. The strain gradient in the rotating electron core wave produces outward radiating Archimedean spiral waves, and with the electron rotating frequency having a high reflective resonance in oscillating space-time, will have over 99% of the outgoing energy in the form of reflected inward Archimedean waves returning back. The presence of both inward and outward waves produces an interference pattern in the form of a rotating standing wave. Beyond the core, these waves decrease in amplitude with inverse radius and never go to zero. Therefore, an electron's cloud of standing waves extends indefinitely. However, rather than a single external reflector, the reflection in the model of an electron is assumed to be the result of resonance with oscillating space-time in which rotating standing waves become their own reflectors. Waves attempting to escape are returned to the core. There are only a few combinations, frequencies, amplitudes, angular momentums, etc. that achieve stability or resonance. These are the stable fundamental particles. Some particles are more stable than others, as explained earlier. The wave-based model of an electron can be broken into two parts. Its core wave, the rotating dipole wave that retains over 99% of its power, and the rotating standing waves. These standing waves surround the core wave and drains about 0.8% of the electron's power. These standing waves are the electron's electromagnetic wave field that includes a second-order distortion from the electron's electrostatic field standing waves, which curves space-time. For the electron, electromagnetic, and gravitational fields, the rotating standing waves are the electron's electromagnetic field, which are linear. They're not distorted in space-time. The electrostatic portion of the electromagnetic field is of interest in this article because it creates a curving of space-time through a second-order distortion of the electrostatic field. The second-order distortion of the electrostatic field waves is a nonlinear effect that scales with amplitude squared of the electrostatic field. The second-order distortion adds a rate of time bias and a volume strain to the space-time oscillators that curve space-time. The electron's electrostatic field and gravitational force are intimately connected. An electromagnetic field from a charged particle like an electron is not a photon. A photon is an electromagnetic radiation that's always oscillating and freely propagating, where the electric and magnetic fields are perpendicular to each other and in phase. The fields associated with charged particles are non-oscillating standing waves and are not freely propagating, where the electric and magnetic fields are 90 degrees out of phase. Now, to understand the second-order distortion, as stated earlier, the two lobes of rotating electron modulate space-time in both volume and time. The differences between these two lobes create a strain on the space-time oscillators, volume, 3 spatial dimensions, and the rate of time rotating frequency. This strain is measured where the sine wave slope of the electron standing waves are at its maximum, which is the zero crossing of the y-axis. Higher strain causes space-time oscillator lobe volumes to shrink and the rotating frequency to slow. The electron's rotating standing waves have both a linear and a nonlinear, which is a second-order component in its electrostatic field waves. Dipole waves in spacetime have a theoretical maximum amplitude strain of 1, which we're looking at AB on the chart. This means that dipole waves in spacetime should also exhibit a nonlinearity that scales with AB squared. The electrostatic field energy in the rotating standing wave is defined as a linear or primary rotating standing wave energy external to the respective Compton radii. An electron's Compton radius is 3.86 times 10 to the minus 13 meters. And AB is a linear strain amplitude. The second order nonlinearity distortion is twice the frequency of the primary wave. This second order distortion is considered the most prominent of the other distortions, like the third, fourth, fifth, etc. This second order strain component electrostatic field creates a positive bias strain on the spacetime oscillators that reduce or shrink their lobe volumes and slow their rotating frequency. This positive bias strain on the spacetime oscillators contracts our three spatial dimensions and slows the rate of time, which slows the speed of light. This creates a curving, or gravity, of space-time by the optical Kerr effect. So how the second-order distortion of gravity curves space-time? It's postulated there is a similarity between gravitational slowing of the coordinate speed of light and the optical Kerr effect that increases the index of refraction in oscillating space-time. This would imply that squaring the electron's electrostatic field strain amplitude should be analogous to squaring the electric field in the optical Kerr effect. The nonlinear second-order distortion of the electron's electrostatic field creates a refractive type strain in the space-time oscillators that slows their rotating speed and contracts their volume. This slows the speed of light and shrinks our three spatial dimensions. The main points are that gravity can be expressed as the square of the electrostatic force when separation distance is expressed as multiples of the reduced Compton wavelength, and the equations relating the gravitational electrostatic forces imply that they both scale as a fundamental function of a particle's quantum mechanical properties such as Compton wavelength or Compton frequency, and all the connections between the gravitational force and the electrostatic force are proposed to be traceable to a quantized dipole wave generating a Compton frequency standing wave in the surrounding volume. Space-time is a nonlinear medium, so a single standing wave has both a fundamental component, the electrostatic, and a nonlinear component, gravity. And gravity has acceleration. It is proposed that the strain in space-time produced by electrons' electric field non-oscillating second-order distortion is responsible for a general relativistic curvature of space-time. An oscillating space-time refractive index, the proposed index of refraction of oscillating space-time, is the change in the index of refraction in space-time equals the wavelength times the Kerr constant, which in oscillating space-time is 1, and then the electric field squared. So note that the magnitude of this nonlinear effect scales with electric field strength being squared. This model of the electron's gravitational strain meets Newton's law of universal gravitation. A prediction is that multiplying electron strain amplitude squared by the electron's Compton radius should give the gravitational distortion produced by an electron. This predicted gravitational distortion is designated as a gravitational radius. This converts to Newton's gravitational equation for the gravitational force magnitude between two particles with an electron's mass. Newton's law of universal gravitation describes gravity as a force by stating that every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers of mass. This is believed to be the first time a gravitational force magnitude has been derived in a bottom-up calculation of the quantum mechanical properties of particles. So how does gravity affect space-time oscillators? This article has shown that gravity affects the speed of light, rate of time, in oscillating space-time by the optical Kerr effect. What may not be as obvious in keeping with the laws of physics is that slower rate of time slows time, the oscillating frequency of the space-time oscillators, and contracts space, which is the volumes of the space-time oscillators. That affects the three spatial dimensions, length, width, height, and both space and time change proportionally, so that an observer or measuring equipment in the same gravity field will not notice or measure a change, so everything stays constant, including speed of light. However, from an outside observer in a different gravitational field would see a change in space-time as gravity changes. The following is a list of some changes that occur when gravity force increases. The rate of time decreases, the three spatial dimensions get smaller, speed of light decreases, and the energy of matter or particles decreases. So how space-time oscillators curve space-time around a mass. Here is a visual representation of space-time oscillators curving around a mass, such as Earth, when gravity affects their rotation frequency and volume. The refractive index of oscillating space-time is increased, which bends and slows the speed of light. This also accounts for gravitational lensing, which is the bending of light caused by gravitational field of a mass. So you see the oscillators visually getting smaller, and what's not shown here is the rotation frequency, but the rotation frequency also gets slower in time. So here's an example of how the gravity affects oscillating space-time around a mass. So here is another example of space-time oscillators affected by gravity around a mass like our Earth. For visual effect, only portion of the space-time oscillators are shown compared to the traditional grid used to show the curve of space-time by mass. Now here's an example of what the inside of a black hole could look like. A black hole in oscillating space-time most likely creates the highest gravity that space-time can handle without time, the rate of time, completely stopping. If gravity force becomes so large that oscillating space-time stops oscillating, which means time stops, and oscillating volumes contract to zero, no spatial dimensions, there will no longer be a wave-propagating medium or oscillating space-time to support waves, particles, forces, gravity, and time. Perhaps just prior to this point of total space-time breakdown, the laws of physics triggers a supermassive black hole to reduce gravitational force strength by emitting high-energy jets of ionized matter accelerated close to the speed of light, which are the relativistic jets. This reduces the gravity and keeps space-time from breaking down. Now, as a summary, this article describes a model of the universe based on John A. Macken's paper, Oscillating Space-Time, the Foundation of the Universe. This quantifies the properties of this medium and proposes that oscillating space-time is the foundation of everything in the universe. Therefore, this single universal field holds the key to unifying all particles and forces. The multiple fields of quantum field theory are characterized as lower frequency resonances and properties of the Planck frequency oscillating medium. The analysis of the proposed electron model interacting in oscillating space-time shows that quantum gravity is derived from an electron's second-order distortion of its electrostatic field standing waves by the optical Kerr effect that occurs space-time. Other particles, such as a muon, would create gravity the same way. This also provides insight into the inner workings of a black hole. Final thought. This model of quantum gravity, with the understanding the effects on the speed of light and our three spatial dimensions and energy, opens the door for a more different perspective on our expanding universe and requirement for dark energy. What if we entertained a thought experiment where just after the Big Bang, when all matter, energy, forces, fields were beginning to form, and there was an additional force that also formed that was a gravitational force not created by matter. This gravitational force could be called background gravitational gamma. This background gravitational gamma would be homogeneous throughout the universe and would be constantly increasing over time. This background gravitational gamma would affect everything the same way that gravity from a mass does. So as this background gravitational effect gamma keeps increasing, time would become slower. The speed of light would slow down more. The three spatial dimensions would continue contracting. Energy of particles would keep decreasing. This would give us the same cosmological redshift that has been interpreted to mean that the universe is expanding. But instead of the universe expanding, all matter is shrinking and time is slowing down since the beginning of the Big Bang. There would be no requirement for the mysterious dark energy required to balance equations. Or could background gravitational gamma define dark energy? I provided references of Oscillating Spacetime, the Foundation of the Universe by John Mackin, a seminar that he provided, a video of his wave-based model, and a paper that he wrote, The Universe is Only Space-Time. And I've also linked this paper to where you can get it. So any comments you have, you can send to me at the comments listed below. Thank you for listening.